Physics Bites,
Physics Bites,
a science podcast in English by the students of Notre-Dame d'Ascension.
Hello and welcome to Physics Bites, the English language physics podcast of the students of Notre-Dame d'Ascension here in Paris. We are continuing with our series with our senior students. We have two students today who are going to talk to us about superconductivity. The best part of the presentation, I think, is that neither of you guys have been doing science for at least 2 years. It didn't prevent you from doing a pretty good presentation, and we learned a lot, and we're hoping to maybe talk about at the end some of the things that you guys didn't have time for you because you prepared so much that it wasn't enough 1 hour of class time to get over it. So let's start with introductions.
So my name is Karim and I'm a student at Notre-Dame d'Ascension in Terminal.
Right, and?
My name is Elisa. Same goes for me. I'm a student at Notre-Dame d'Ascension.
So neither of you guys have done sciences officially since 2 years ago?
2 years ago.
And
10th grade.
Yeah.
You miss it?
Partially.
Yeah. Maybe physics, not math.
Well, math isn't a science, but we'll leave that for another time. So, superconductivity. Let's get right into it. What is superconductivity? Maybe we can go over a bit of like what it is and then how we discovered the phenomenon, and then we'll maybe get into some of the actual technical details.
Sure.
All right, Karim, you want to get us started?
Yeah. So superconductivity is a phenomenon where certain materials conduct electricity with zero resistance, and its specificity is that it happens below a characteristic critical temperature. Which means that the current flows indefinitely without losing any energy as heat.
Right, which is a really, really impressive thing, important thing, and shocking thing, because as long as we've known electrical systems, there's always some sort of a resistance. Mm-hmm. Sometimes it's good, we use it to create heat. Sometimes it's bad because it makes us lose efficiency and electricity. And the discovery of superconductivity was quite shocking to see that there are certain situations, certain configurations of matter where we can actually have current go on forever without losing any energy, right? So we can instantly think about all the amazing applications it could have. So when did we discover this phenomenon? How did it happen? And then we'll get into the science a bit.
It all started in 1911. So when a Dutch physicist, he was called Huyck Kamerlingh, he cooled mercury down to just 4 degrees above absolute zero, which is about 269 Celsius degrees, minus 269.
Right.
And it's way cooler than outer space.
Or at least comparably cool, right?
Yeah, exactly. And he found out that the electrical resistance, it just dropped to zero. And that's when he realized that he accidentally discovered superconductivity. Right. Now, fast forward in 1933, two German physicists, this was Ostenfeld and Meissner, they discovered that superconductors don't just carry electricity perfectly, but they also repel magnetic fields.
Right.
And that's the famous floating magnet that we mentioned in our
which carries the name of one of the discoverers.
Yeah.
Which
is the Meissner effect.
Right, the Meissner effect, which is usually the image that we see on everything as soon as we talk about superconductivity. It's a little cube that's floating and it's sort of like misty air over a magnet.
Yeah. Okay. That air comes from cold temperatures.
Right,
yeah.
Exactly.
And so a bit later, in 57, for decades no one could do anything, no one discovered and no one understood why all that happened, why the levitation, why the Meissner effect. But in 57, 3 physicists, Bradeen, Cooper, and Schiffer, they cracked the code. They made a theory, BCS,
right.
Named after their names.
Yeah, right.
Exactly. And they explained that the electrons in a superconductor pull up and move together in sync. Right. So they're like a perfectly choreographed dance. And
these pairs of electrons, what are they called?
Cooper pairs.
Right. This is the C in the BCS, so we call this Cooper pairs, which is like the starting basically point for understanding superconductivity. Okay. Mm-hmm.
And a bit later, in 87, they discovered that that there is a side of superconductivity that is much more interesting, and we still have stuff to find out about it as of today. It was the ceramics.
Right.
So they work much higher temperatures, around minus 180 Celsius degrees.
Which is still really cold, but
it's really cold,
much hotter than
it's much
minus
hotter.
269.
Exactly.
Right.
Exactly. And
which means easier to create conditions for
and it was easier to achieve
Right.
because before they used liquid hydrogen, which is also very expensive.
Yeah.
And with to reach higher temperatures,
Right.
they used liquid nitrogen,
Right.
which is much cheaper as well.
Right. We use it already for a lot of different things. Okay.
And so that opened a big door to many more applications and many more discoveries to come.
And sort of the holy grail of superconductivity would be able to do what? Because I mean,
Well, that's
It would be to get room temperature superconductors because you wouldn't need all the cooling equipment and dust, so it will be very efficient to have in many feet.
right, because then we can easily use it for everyday life for a lot of things without, as you say, the need for the equipment that goes around, which is basically necessary for the cooling.
because right now we have two different types. As we said, the type of superconductors that work at very low temperatures, but they don't hold
Okay.
as long. It's the resistance. It's kept inside, but it just suddenly breaks, and they're called all or nothing. And then the second type of superconductors that are also used in applications, which Karim is going to get more into.
Right, we didn't get to necessarily get too much into it, but yeah.
The second type of superconductors are the HTS.
High temperature
High temperature,
superconductivity. Yeah.
yes.
Okay.
And they're usually ceramic compounds and copper compounds.
Okay, so this is one of the more recent, I think we can call it more recent discoveries in physics.
Yes.
It's a 20th century discovery, and the actual explanation of it goes back 60, 70 years, right? As an interesting side note, the B in BCS, John Bardeen, is the only guy who's had 2 Nobel Prizes in physics. The first one was for the invention of the transistor, right? So he had a hand in a lot of really big stuff. Okay, so maybe I'm going to turn to Karim, because you were the one who sort of talked to us about this whole idea, which is central to superconductivity, the idea of zero resistance, and then you talked a little about these Cooper pairs. I know it's not easy to talk about this without blackboards and without images. Let's just get to the heart of the topic, and then we can move on to some of the more easy to talk about subject.
So maybe I can give sort of an image. So let's say that a regular metal wire is like a busy hallway, and you're an electron trying to move through all the students, but you keep bumping into them, so you lose energy because they're vibrating all over the place, and these collision, so they slow you down, and they release heat, which is
you lose energy and it becomes heat, right? This is the famous Ohm's law that you guys and the Joule effect that you guys studied in many years ago when you were in middle school,
and we still do it today in
oh, you do it in
Okay.
okay.
And so
Science for poets, as we call it, right?
Shortcut.
And that's what resistance pretty much is. And what a superconductor is imagine that always gets really cold. So all the students, which are the atoms, stay in the same place. It allows you, as the electrons, to glide through without hitting anything. So you don't have any friction, you don't lose any energy, you don't release heat, and so there's no resistance.
Okay. So that's a good, I think, visual way of thinking about what happens when we have superconductivity and when we don't. So let's get right into the nitty-gritty and the technical details of it. You talked about these Cooper pairs. Nobody can start any course on superconductivity without hearing Cooper pairs. What are Cooper pairs, and why do they play such a central role in the explanation of the phenomena?
Well, normally electrons they repel each other, but in a superconductor the electrons they slightly distort the atomic lattice, and so when the atoms are distorted by first electrons, a second one is attracted to the first one, so they form like kind of a bond, which is called a Cooper pair. and so they move along in the lattice in a coordinated way, and they don't lose energy, and they can keep going pretty much forever as long as it's still cooled to a certain temperature.
And these Cooper pairs is the formation of these Cooper pairs is what is dependent on the temperature, right?
Yes.
We don't see Cooper pairs forming at high and pressure. Okay. So at the beginning, we were able to do this only in very, very, very cold settings, and then the idea is that we're finding different ways of forming these Cooper pairs, which doesn't depend so much on like very extreme temperatures. And what is the warmest? Just out of curiosity, what is the warmest superconducting material that we've ever tested? Do you guys know?
I'm not sure about the material, but I know that they achieved minus 23 Celsius degrees.
Okay.
And unfortunately, it was under extremely high pressures.
Yeah, okay.
Yeah.
I was looking at minus 23, I'm like, in Canada, we could maybe start using superconductors,
No.
but the pressure is not high enough.
Very viable.
Okay. So, Elisa, the other very hallmark part of superconductivity that you brought up was this famous Meissner effect. And you talked about how this discovery 20 years after the original discovery of this lack of resistance was quite interesting in that it showed that there's also something happening in superconductors when it comes to magnetic fields.
Mm-hmm.
Do you want to maybe give us just a brief description of what the Meissner effect is and maybe try and...
Well, as I've said before, I'm not finding my words.
It's okay, it's okay.
So, usually, they work until, the magnets repel each other.
Right.
And in superconductivity, as there is no loss of energy as well, there is higher
Repulsion?
Yeah, repulsion.
Okay.
And so it lasts longer as well.
Okay.
And this is why we can achieve things such as the maglev trains, which only work through friction. And also the friction is very little.
So if I understand correctly, what happens is when we end up cooling this superconducting material, when it reaches that critical temperature, because of the superconductivity, it doesn't accept magnetic lines, the magnetic field lines from a magnet to go inside it. And that rejection, this repulsion is what makes that levitation happen.
In the low temperature superconductors, the thing is, we call them all or nothing because it works until a certain point. And if, let's say you bring a magnet too strong, that resistance is broken. And so they just clash together.
Okay.
And this is why machines in which we use superconductors need very high maintenance because
it's not stable in a way.
Not stable, and
Okay. And this Meissner effect, this sort of levitation because of these properties, is it something, we'll get into the application, but is that one of the major applications of superconductivity when we come to...
Pretty much. For example, in the maglev trains,
magnetic levitation,
which we'll be talking about later on. It's used for the core principle of how this train works. So it's levitating. It's above the tracks, so there's no friction, no energy loss, which allows you to go much faster and in a greater distance with less energy.
Okay, and this was kind of the idea that was behind projects such as like the Hyperloop thing, and the idea of having you have this magnetic levitation, but you also put it into vacuum, so there's even no mechanical friction from the air or anything like that. Okay. Maybe we can very quickly go over what you mentioned. You talked about there's like two types of superconductors, and you said that there was the discovery of a certain kind that came later in the 20th century. Maybe we can just very briefly go over what these types are.
This was the second type of superconductors, so the high temperature ones,
right?
And the low temperature, the low temperature ones are the ones that are less reliable.
So, and you mentioned something about the first kind being more just like very pure metals that behave this, whereas the other ones are more sort of alloys. Okay. So alloys allow having superconductivity at a higher temperature, but if we're just taking an ordinary metal like lead or mercury or tin, you can have superconductivity. It just has to be in very cold conditions.
Yes.
Any metal can be a superconductor if it's cold enough in a way?
Yes.
Okay.
But it doesn't last for long, which is because the
not really
pressure.
advanced.
So extreme conditions and unstable.
Yeah.
Okay.
Well, at least it is very stable in the state of superconductivity, but it doesn't stay in that state for long, and so when it crashes, it just crashes.
So you can't actually have any proper
Yeah,
applications.
it's mostly used for experiences, and which is why it was very practical.
Right.
When they discovered it, they could play.
So you can do it in a lab in like
Exactly.
small quantities to study the phenomenon.
Cost effective also because it's like cheaper metals. Which
Right, you don't have to create those alloys.
Yeah.
But with alloys, you said that it can be much more stable, it can be more usable at a higher temperature. Do we use alloys in any sort of a thing already for these superconducting alloys? Or can you give us an example of like what kind of alloys we're talking about? Is it like really weird combinations of metals or?
Well, I have an example in my mind. It's the YBCO, which is copper and ceramic compound.
Okay.
It's yttrium, barium, copper oxide.
Right.
And it is based on ceramics, and so it's a...
What do you mean by ceramics in this context? Because in my mind, I'm thinking like alloys are mixtures of metals. We have elemental metals, mix of metals, and then you're talking about ceramics.
It's very brittle texture, and so it's also why it's very expensive to work with. And that's the case.
It's a sort of a mix of a metal with a non-metallic substance.
Yeah.
Is that kind of it? Okay.
Yeah, and also which is weird about this compound is that at room temperature it's an insulator, but when you cool it down really far, which it then becomes a superconductor. So that's why the properties are really weird and depending on the temperature.
Okay, so we in a sense use the word alloys and ceramics interchangeably? It kind of means the same thing, or not all alloys are ceramics, but all ceramics are alloys?
There's you can usually find copper in almost all of the high temperature.
Okay, that's it. Well, that's a good news because we have lots of copper and it's pretty cheap, right?
It's cheaper.
Yeah.
Okay. Is there like a critical temperature which we consider as if we're higher than that, it's an HTC, and if it's under that, it's LTC, or?
Usually it goes around 70.
Like minus 70 degrees or something like that, or 70 Kelvin.
Yeah.
70
Exactly.
70.
70 Kelvin. That was.
I think in your thing you were talking about 30 Kelvin, but I think it might be.
70 is for the low temperature ones.
Okay.
Everything around that temperature.
Okay.
And it's about 180 Celsius degrees for the high temperature.
And you mentioned the importance of copper and copper oxides usually for most of these high temperature alloys and ceramics. Yeah. Okay. So I think it's difficult to go into more technical details without visual aid. So let's go into maybe properties and like what are the limitations, what are the challenges with using these, and then we can get into some applications once we've sort of developed the boundaries on that.
Well, as we've said before, they are very high maintenance, and it is also why it's expensive to take care of them, because putting, for example, in wires, they can be used in wires to make faster,
better current conduction, yeah.
Exactly. Well, they need high maintenance. Putting them in wires requires very specific utensils, not utensils, but material and
machinery.
Machinery, yes.
Right.
Thank you.
So the fabrication process is not necessarily easy
very
nor cheap.
Expensive.
It's very expensive, and it's because they have to be really thin and very well protected.
Okay.
It's because the material is naturally brittle.
It's very brittle.
It's not as easy as it
So
is.
we could use it, but we have to use it in situations where it's easy to sort of control it, and it's well protected.
Why they're not publicly available.
Right.
I mean, to an extent, for example, in the MRI machines or...
Right.
Magnetic levitation trains or something.
Right. Which is not stuff that the general public actually gets to, like, open up and play around with the wires, right? So it's very controlled conditions. Okay. So you talked about a few of the challenges with the use. So you talk about the actual sort of the material properties of these kinds of more usable HTCs. You mentioned there's problems around cooling. There's problems around the question of quenching, which maybe we can define here, and stability. Let's talk about the cooling maybe challenges, and then we'll go into the follow-up.
Well, as we've said before, we don't know how to achieve yet, at least, room temperature superconductors, because if we were to achieve that, that would be really revolutionary in science, because we would be able to put them to public use. And actually, I believe that there was in Paris, it was they replaced some cables, a great deal of cables, because they couldn't add any more, and they replaced them with 2 superconducting cables. At Metro.
Okay, so given these limitations and stuff, there are still, you found some applications outside of just the machines, such as MRI machines, maglev trays. You found something about something we did in Paris recently, which was a world first?
It happened in 2023.
Pretty recent.
At Gare Montparnasse, so
right next to where we are.
Yeah. The world's first superconducting cable was installed in a railway.
Okay.
It was because there were 2 small superconducting cables that replaced a great number of other cables because they didn't have any more place for adding more cables, and they were just placed there.
As a proof of concept, I guess, of the
as well as concept of utility,
right? Because it could be quite revolutionary, like you guys mentioned, in how much it can be, because you lose no energy, you can make things 100% efficient, which is kind of a dream for any engineer or scientist, if we can. Okay. Quenching and stability issues. Just very briefly, because since we're going over the list of limitations of superconductive materials, what is that all about? What do we mean by quenching? What is the link with stability?
So when we make a superconducting cable, it requires, as we said before, specialized manufacturing. And there is a limit, and if we push the current if we push too strong a magnet, I more or less said it before, but probably I didn't explain it enough. If we push too strong of a magnetic field through a superconductor, it can suddenly lose all its superconducting state.
Okay. And this has a name. This is called
quenching.
Quenching, right?
Yes,
it's just a sudden loss of superconductivity.
So in a large magnet, that's a dramatic event, because huge amounts of energy they release heat, and so it's to the point of boiling hot, and so it's boiling off any coolant, and and for machines or anything that's under high pressure, that can cause explosions, and that is not good.
No, we want to avoid explosions as much as we can.
Definitely.
Especially in MRI machines in hospitals.
In MRI machines. So you guys probably wouldn't remember, because you guys were probably 1 or 2 years old at the time, when the particle accelerator LHC came online in 2008, 2009. There was an issue, because here you have these giant magnets which create super powerful magnetic fields, and you can only do that with superconducting materials. And it's going around 27 kilometers, right? So imagine an MRI machine like for 27 kilometers. And it's all cooled with liquid helium. And you're creating currents that go up to like 14,000 amperes. And apparently there was an error in some little part, in that because these metal parts are sort of welded together, this is very special welding techniques, and there was one little part where it was not superconducting, and they turn on the machine and you have this like 12,000 amperes going through. Everywhere is perfect. In one place it's not perfect, even with like a nano ohm of resistance or whatever, and obviously instantly it creates a lot of heat. it makes expansion of the helium gas, which is at like 3 Kelvin or like minus 271, which is a superfluid which can go through any little cracks. It goes out, explosion. 15 years of work has to be put off for another year. So it was quite the thing, and it's just this, like you said, like we can't afford to have quenching in a machine that we're going to use because it could be quite disastrous. So I think that's a good segue to going to talk about machines that we can use, right? So let's talk about a few applications that are existing, maybe a few applications which are maybe to come or whatever.
Well, the most common application that we have in today's world would be the MRI machine,
Right.
which stands for magnetic resonance imaging. So it's in hospitals, and it's a technique that uses strong magnetic fields and radio waves to produce detailed images of the inside of your human bodies.
Right.
When you do a scan, etc.
Right.
And so the heart of this MRI machine is a powerful superconducting magnet.
Right. Which is creating that magnetic field, which allows us to see the different tissues, right?
True. So, to give an example, an MRI machine operates at about 1.5 to 3 Teslas.
Which is the magnetic field strength.
Yes, and in comparison, the Earth's magnetic field is around 50 microteslas. So it's about 30 to 60 times, 1,000 times higher than the
Million
Earth's
times.
magnetic fields. Yeah. So to maintain such a strong field stability, the magnet's coil is made of superconducting wires, which is niobium titanium, and the coil is kept at around 4 Kelvin, so pretty much 269 degrees Celsius.
Liquid helium as well, I think, usually.
Yes, it's immersed in the liquid helium, and so it stays superconducting. And in operation, a large current, which is hundreds of amps, flow through the coil with no resistance and create a steady high magnetic field.
Right. We could do that with non-superconducting materials, but it would consume... It could be done with non-superconducting materials, but the amount of energy it would require and the amount of heat it would create, I would imagine, would be quite something.
Huge, like it requires megawatts of power to run the machine.
Right, so not possible. So that's one machine that would not have been possible without superconductivity, right? Which is kind of the sort of thing we're looking for. What else do we have as far as applications go that currently are being used outside of just the sort of medical...
We also have in the transportation field the maglev trains.
Right.
So, if I'm not mistaken, it's mostly in Asian countries like Japan.
Right. And I think China as well.
Yes, so there isn't one in Europe for now. But the most known one is the Japanese CS maglev, and maglev stands for magnetic levitating.
Mm-hmm.
And so the train, as I said before, floats above the tracks with no physical contact, which eliminates friction from the wheels that we have.
Or any sort of a mechanical system which has mechanical friction.
So it's achieved with powerful magnets, with the repulsion and the traction between those magnets and the guideway that propels the trains above the ground. And so some maglev trains use conventional electromagnets, but the fastest design use superconducting magnets to reach higher performance.
Mm-hmm.
So
I guess that requires a lot of superconducting materials if you want to like lay down railways that would go like hundreds of kilometers. So
that's why it would be useful to have a room temperature superconductors.
So there's really the economic factors, I think, and the manufacturing factors are what's creating these limits. So in a way, outside of sort of esoteric uses such as particle accelerators, maglev trains, of which there are not that many, MRIs are basically the one major application that we have currently kind of everywhere in the world.
True. And what would be coming next would be those cables like we talked about in Montparnasse that could replace our typical cables and have much higher performance and in the long time lower cost also to produce if we achieve room temperature.
Where are we with room temperature like applications? Because I mean, you talked about the minus 23 degrees, but you said it requires really, really extreme pressure conditions. I don't think that the ones we use for some of these other applications are not that cold, but still.
Well, as Karim said, we're using liquid nitrogen right, in MRIs, so it's not that cold. But anything above minus 180 Celsius degrees, it's really hard to achieve as in terms of practicality.
Stable long term.
Yes. Yeah. But given today's circumstances, we make discoveries every single week, and so it is to be expected that we find something that works rather sooner than later, I guess.
But given especially the last couple of years with the increased electrical usage with our data centers, which are just sort of popping up everywhere like bacteria, we are using more and more. So I mean, it would be pretty useful, I think, economically in terms of climate, energy,
advancement in technologies and like pretty much every field that because we use electricity pretty much everywhere. Yeah. So having
and we want to electrify even more the system, right? Because for climate reasons.
Because it was already a revolution when we first discovered simple and low temperature superconductors, even if they weren't in practical use. It was an entire revolution.
Right.
And, if we are to discover and go deeper into that field, it's again.
I tell my students, like, if you want, this is all part of material science, condensed matter physics, material science, which is not the most, I guess, glorious or sexy domain of physics, but it has a lot of practical uses and
it has a lot of prospect.
Because it's all about applications at the interface of the theory and a lot of applications. You could actually get rich from it, right? For those of us who are more inclined.
If there's a breakthrough, sure. Why not?
No, but maybe we're thinking, this is just an idea, but maybe when we were thinking of sci-fi and the levitating cars, maybe that's how we might achieve that.
Who knows? We can only dream, right? And hope to train more students to go into something like this. Okay, well, I think we've gone over the topic as well as we can in an audio setting. Yeah. So, like usual, I'm going to ask you guys a question. It's especially for you guys, which have sort of put aside your scientific side of the studies. How did you find the topic? Did you find it interesting, difficult?
I found it really interesting, first of before anything else, and it wasn't as hard as I thought it was to understand. We did go a bit into detail with the presentation. As much as we could, because if we were to go, we didn't have enough.
We could go deeper, but it would be much more complicated.
Right, and I think that wouldn't be the point, right? The point is to have a general understanding and sort of just increase our knowledge on the topic. No, it's good because it is not something that is easy. It's not something that
it's not something that it's talked about.
No, it's not something we would talk about in school, right? It's just because it is
school, maybe less in papers.
But we should.
Generally speaking, it's not.
So when you'll have a chance,
topic from someone who doesn't do science.
So when your future administrators or in some sort of a capacity to make decisions about what to finance, you're going to be pushing to finance material science and
well, it's a loop. If you invest in that and you could get a lot of economical benefits from this, you get your investment back. And
listen, he's already talking like the prospect is the doctor for tomorrow. All right. Well, thank you, Karim and Elisa. The topic was very interesting. You guys did a really, really good job of not so easy to present topic. Like you said, that is not necessarily the most well-known of the physics stuff. So thank you very much.
Thank you.
It's our pleasure. Thank you.
So, that is Physics Bites for this week. We hope that you enjoyed this episode, and we would love to hear what you thought about the topic in the comments section. If you did enjoy the show, then subscribe to our podcast, share it with your friends, and be sure to leave us a 5-star rating on whatever platform you're listening on. And more important than all of that, come back soon for a new episode.